In this section, I'm going to study some rules of differentiation, which could also be called rules for computing derivatives, because this is really used for practical computations to do with them. And as a first thing, we want to study how differentiation behaves with respect to these algebraic operations that we already studied. So sums, products, and so on. And this leads to some equations that are probably familiar to everyone who saw or learned about derivatives in high school. So we investigate the behavior of algebraic operations and derivatives. Okay, let I be an interval, let A be a point in I, and let f and g be two functions from the interval to C, and both are differentiable in A. Okay, then we have some computational rules. Okay, the first property is basically what you call the linearity of the derivative, which will kind of make sense basically later on when we learn about linear algebra. So the sum f plus g from I to C, the sum of the two functions that we've seen before, this is again differentiable in A. With derivative simply given by the sum of the two derivatives. So f plus g prime of A is f prime of A plus g prime of A. So we can just take the derivative sum-wise and then sum them all up, which is an easy thing to do. Then for each constant factor lambda in C, lambda times f, which is again of course a function from I to C, is differentiable in A with so lambda f prime of A is simply lambda times the derivative f prime of A. Okay, so this is probably what you know from high school, that summing it multiplying with constant is just well behaved, so we can just take the summands individually. Okay, now we come to the more complicated rules. The first thing is the product rule, sometimes also called Leibniz rule. And probably I should call it Leibniz rule because Leibniz was indeed a professor at the University of Leipzig. But anyway, I call this product rule. So the product of the two functions from I to C, this is again differentiable in A. And the derivative has this interesting property that f times g prime of A, this is now not that straightforward as before. This is f prime of A times g of A plus f of A times g prime of A. Okay, so this is also something that you just need to memorize at some point. Then we get the quotient rule, which is actually a hidden product rule, but it's useful to memorize this on its own, the quotient rule. So if we assume that g is non-vanishing, so g of x is not equal to 0 for all x in I, then the quotient, this is what we need to have f divided by g well defined. This is now a map from I to C. This is again differentiable in A. In A, and for the derivative there is also a formula, f divided by g prime of A is given as follows, f prime of x times g of x minus f of x g prime of x, and the whole thing divided by g of x squared. Sorry, A, not x. Yeah. F prime of A times g of A minus f of A g prime of A divided by g of A squared. Sorry. Okay, let's prove them. So first of all, the proof of part A is very simple because I will definitely not give it in here because this basically follows from the properties of limits of functions. We've seen that the derivative is defined as limit of functions, and for limits of functions we've already seen that the limit of a sum is the sum of the limits if it's convergent, and same with constant factors. So part A, here it is again. So it's just these two simple properties. They follow from the properties of limits of functions. So follow from the corresponding properties of limits of functions. And let me just look up, theorem, functions. This was theorem 3.50. Okay, this is just nothing to be worried about. So the product rule now, here, this requires a bit of work. So let's do this. This is basically really a straightforward computation. We compute. So f times g prime of a. This is by definition the limit for h going to 0 of f of x plus h, a plus h times g of a plus h minus f of a times g of a divided by h. Okay, it's just a long formula, but anyway. Now, we kind of add a term and subtract it artificially, namely this is the same as the limit of h going to 0 of f of a plus h g of a plus h minus f of a plus h g of a plus f of a plus h g of a, okay, minus f of a g of a. Sorry for messing up the fraction here, so just subtracting a term and adding it so nothing happened. So divided by h. Okay, now we split this up into two, namely the first two, here we can factorize f of a plus h, so this is the same as the limit of h going to 0 of f of a plus h times g of a plus h minus g of a divided by h. And for the last two here we can factorize out the g of a. So here we get, this is plus f of a plus h minus f of a divided by h times g of a. Okay, now take a look at this. This is something constant, this doesn't matter. This here is the differential quotient of, if we pull the limit through, this is the differential quotient for h, for f, and this is the one for g. And about this factor here, this means this is just the limit for h going to 0 of f of a plus h. So this means if h goes to 0, this will go to f of a, because since f is differentiable in a, it's also continuous in a. Here we need the continuity that we showed in the last corollary of the previous section. So this is, so all we need is corollary for 8, and that f and g are differentiable. So corollary for 8 was the continuity here. This is the limit of, and now this is now for the standard rules, I'm not quoting that theorem, but the rules for limits of functions. This is limit of h going to 0 of f of a plus h times limit of h going to 0 of g of a plus h minus g of a divided by a plus the limit h going to 0 f of a plus h minus f of a divided by h times g of a. Like this. And now we see, since we're differentiable here, so this is f of a, this is g prime of a, this is f prime of a, and finally g of a. So we get what we wanted, except I reordered the two summaries since I find it easier to memorize the other way around. But of course this doesn't matter. Okay, this shows the product rule already. Now, for C, the quotient rule. Then we take a special case. First consider the case that f of x is equal to 1 for all x in I. so the quotient of 1 and the function g. And now we can basically use the same computation, almost the same computation as we did in the previous video. That's the one I edited in for the function 1 over x. Namely, we do the following. So 1 over g prime of a, if it exists. This is the same as the limit of h going to 0 of 1 over g of a plus h. Oh, sorry, I've somehow, no, okay, I thought I messed up the notation, no. 1 over g of a plus h minus 1 over g of a, and this divided by h. Now, similar as in the previous proof, I now bring these two into the same denominator and move the denominator downstairs. Then we get at that point that this is g of a minus g of a plus h. So the first one is from expanding this, the second one from expanding that. Oh, and I forgot the limit. Okay, and this divided by h times g of a, or g of a plus h, let's keep this order, times g of a. Okay, now, let's reorganize this. This is the same as the limit of h going to 0 of, and now I will just change the notation a slight little bit. This is minus g of a plus h minus g of a divided by a, and this whole thing multiplied with 1 over g a plus h, g of a. Okay, and if we now take a look at these two separately, here we can again use that g is continuous and that it's differentiable in a, and here that is continuous in a. So this is the same, so this is only using that g is differentiable in a. That this is the same as minus the limit of h going to 0 of g of a plus h minus g of a divided by h times the limit of h going to 0 of 1 over g of a plus h times g of a. And here we see this is, of course, g prime of a, just by definition. And here we see, again, since this is continuous, if h goes to 0, this thing goes to g of a, and so then we get that this goes to g of a squared. Okay, so this kind of, it makes sense. This works with the product rule because the other, with the quotient rule, since the other term in the quotient rule would vanish if this function f is constant. Okay, now we do the general case, assuming this, and we just need this and the product rule to derive the whole thing, as we shall do after I erased. Okay, we've checked the formula for the function 1 over g, and now we get the general picture, because if we want to derive f over g in the point A, this is of course the same as deriving f times 1 over g of a, which is now a product of differentiable functions. For 1 over g we've seen the differentiability, and by the product rule, this is, so this was part B of the same theorem here. This is f prime of a times 1 over g of a plus f of a times 1 over g prime of a. So this formula is what we've computed, so let's just insert our result. So the first thing is just f prime of a divided by g of a. And the second part is plus f of a times minus g prime of a divided by g of a squared. Okay, so this is of course, and let's just multiply this. So this is f prime of a divided by g of a minus f of a g prime of a divided by g of h squared, and now we see that we have already achieved it. We just need to expand the first fraction by g of a, and then we put them onto the same denominator, and so we get f prime of a times g of a minus f of a g prime of a divided by g of a squared. Okay, and this completes the proof. Okay, So these are now the kind of important rules for our functions with these algebraic operations. And so let's see some examples for this, of some applications of this. Okay, we start very simple. We take a polynomial. Every polynomial, let's say P from R to R, P of x is the sum of some from 0 to n for some number n, a k x to the power of k. So we've seen that each x to the power of k is differentiable. That was part of the theorem containing the examples. And now we've shown that sums, so sums of two functions, so also sums of finitely many functions, by just iterating this, are again differentiable, and multiplying with some fixed numbers also doesn't matter. So this means that by this part A is differentiable. And we just get that the differential, the derivative at the point x is simply the sum of the derivatives of these guys. And so by this constant value property, so it only means we need to derive these guys. And everything, can just leave everything as it is. And we see that for k equal to 0, this is just a constant term. And we've seen that a constant map has derivative 0. So this vanishes. And so we still get the sum from 1 to n. And then derive everything. And this is just a k times x to the k minus 1. This is the general formula to derive polynomials. Okay, so this was an example of linearity, and so now let's do the quotient rule, or basically, first of all, I want to give the basic case. Let's consider the function from 0 to infinity to r. F of x is 1 over x to the power of n. So we've previously seen the derivative 1 over x. Now we increase this by, so we just add some exponent in the natural numbers. So this is of course the same as x to minus n, just to say this. Okay, this is now 1 over x to the n. We know that x to the n is differentiable. So this is basically this basic case of the quotient rule that I've already erased. So this example of 1 over g. So here by the quotient rule, we get that f prime of g, so this is now in this case just minus, and now the derivative of the denominator, which is x to the n minus 1, divided by the denominator squared, so x to the n squared. This means we get minus n x to the n minus 1 x to the power of 2n, and now we can of course just cancel these out. This is the same as minus n divided by x to the power of n plus 1. And if we write this as minus n times x to the minus n minus 1, we basically see that since the original function was x to the minus n, this is the same as the derivative for polynomials, where we just pull down the exponent in front and subtract your exponent to get the new one. So subtract 1 from there to get the new one. And so this is, this shows basically for these guys, this formula generalizes. We will see in a little bit that this generalizes even further. We will see this in the course of the section. But here we see that this generalizes at that point. Then I want to derive another elementary function, which we have seen, which we have defined as the quotient of two functions, namely the tangent. So the tangent is defined from minus pi over 2 to pi over 2 to r. Okay, this was sine over cosine, and we've seen that the cosine is not vanishing, so this is well defined. So this function here is then differentiable by the previous theorem, since sine and cosine are differentiable, and we can compute the derivative. So the derivative of the tangent, tan prime of x, this is now, if we want to write this as a quotient of function, this is sine over cosine prime of x. So what do we get by the quotient rule? We get, the formula is here. So this formula here, so first f prime g minus fg prime. The derivative of the sine was the cosine. This is what we've seen. So f prime is in this case the cosine times g, which is also the cosine, minus, and now we just take f, so the function in the numerator, times the derivative of the denominator, and we've seen that the derivative of cosine is minus sine. divided by the square of the cosine, which we have denoted by cos square x. Just cos we can. Okay, this can be simplified. So the first part is just cos squared of x. And this is minus minus, so we get a plus sine squared of x divided by the cosine squared. And of course, sine squared plus cosine squared is always 1. So this is actually surprisingly simple, I would say. This is just 1 over the square of the cosine of x. So this is the derivative of the tangent. Okay, so there's one more important rule that's sometimes I know that in Germany sometimes people learn it in high school and some even don't. The chain rule. I think, most people I think should see this in high school, but maybe I'm overly optimistic. So, theorem 411. This would actually be interesting. Maybe if you see this video on YouTube, maybe write in the comments if you've seen the chain rule in high school. I would just be interested. So, the chain rule. I mean, it's really interesting, and this is also what makes this course so special, since I've got people from all around the world in one course, and you have all different backgrounds, you've all learned different things in high school, and I know that in some countries people learn a really impressive amount of stuff in high school, and some people don't. So it's, it's always interesting to see for me. Okay, we take two intervals, I and j. They are just intervals, and then we take a function f on the interval I, from I to R, and g from j to R, and assume that f of I is a subset of j, such that we can define the composition of these functions. And this is what we're interested in now, the derivative of a composition of functions. Okay, if we assume that f is differentiable, so if f is differentiable in A, and g is differentiable in f of A, then the composition g composed with f from I to R is differentiable in A, and there's a nice formula for the derivative. G composed with f prime at A is g prime at the point f of A times the derivative of f at A. It's kind of the most beautiful results I know, I think, in analysis. I really just like this. Okay, I mean, it's kind of, you have to appreciate, you have to see some examples or made some computations to really appreciate this, but maybe you will at some point. We will see. Okay, let's prove this. We will need this characterization of differentiability that I gave in the last section, so that we can kind of characterize the differentiable function as by some continuous function such that the function is a constant value plus a continuous function times x minus a. This is kind of easier written than explained. So since g is differentiable in the point f of a, this was theorem 4.6, so these equivalent characterizations of differentiability. There exists a function r on j, from j to c, which is continuous in A, sorry, not in A, but in f of A, which is the point we are now considering, continuous in f of A, such that at the point f of A, r is simply the derivative, so g prime of f of A, and such that g of y for some y in this interval is g at the point f of A plus r of y times, and now y minus f of A, the point we are referring to. This f is probably a bit irritating, but this is just if we consider the fixed point f of A. Okay, this is now basically just the theorem 4.6, and this is what we will use. So if we have this, so this holds for all y in j. In particular, since f maps from I to j, this means that for all x in I, with x not equal to a, we consider the following. We consider the quotient g of f of x, which is f of x is in j, so it's well defined, minus g of f of a divided by x minus a. So, and if we take a look at this, if we here would take the limit of x going to a, this is the differential quotient, right? This was this alternative characterization, differential quotient for g composed with f. So this is actually the thing we want. So if we now insert this here with y equal to f of x, this means that this is the same as r of f of x times f of x minus f of a divided by x minus a. And this is, of course, we just write this in a more convenient way, r of f of x times f of x minus f of a divided by x minus a. Okay, now we can see where this goes. If x is now going to a, this here is the differential quotient then for f. And we know that this exists. This was the assumption f is differentiable in a. Also, we knew that r is continuous in f of a, and so then you can see since f is continuous, that's kind of the computation that I will skip, you can see that this is actually going to r of f of a. And yeah, since r is continuous in f of a, f is differentiable in a, this implies that g circ f prime of a, which is the limit of x going to a of this quotient, so g of f of x minus g of f of a divided by x minus a. This is now the same as the limit of this, and this is, you can already split this into two factors. This is limit of x going to a of r of f of x, and the second guy, limit x going to a f of x minus f of a divided by x minus a. And as I just said, this is, here we can use the continuity. Here this is the differential quotient, so this is r of f of a times f prime of a. And as we saw above, r of f of a is just at this point, this is simply g prime of f of a times f prime of a. And here we have the formula that we wanted to show. So, done. Okay, I will give you an example of this after erasing. Okay, let's do a simple but famous example, namely example for 12. F goes from r to r. F of x is e to the minus x squared. This function is quite famous. This is the Gaussian distribution or the normal distribution. The graph of this function is this bell curve that you might have seen, and that's very important in probability theory. So if you have 1 and 0, the graph of this function would be like this, and here approaching 0, and here approaching 0. Okay, this should be symmetric, but this is the idea, so it looks a bit like a bell. Yeah, it used to be on the, actually before there was the euro, the Deutsche Mark, the German currency, on the 10 mark bill, which was approximately €5 today, there was a picture of Gauss and there was this bell curve, because they had famous German scientists and so on, and writers on the notes. But anyway, I'm an old man, I remember this. Okay, let's see this. So this is now really a composition of functions. Namely, this can be written as g composed with h, where h, the first part, is minus x squared. And then we just take minus x squared, and afterwards we exponentiate. So g of x is x of x. Okay, we have seen that these two are differentiable. So by the chain rule, yeah, f is differentiable, and we can compute the derivative. F prime of x, this is now g prime of h of x times h prime of x. So this means we have x prime of h of x, which is minus x squared, times the derivative of minus x squared, which is minus 2x by this computational rule we had before. And of course the x prime, we've seen that this is simply x itself, so this is actually e to the minus x squared, so we get minus 2x times e to the minus x squared. Right? It somehow makes sense if you think about this tangent viewpoint, because if you now take a look, if x is a negative value, this would be, so I mean this number is always positive. So if x is a negative value, this is positive, and this means kind of if you think of this tangent, the slope would be increasing, which makes sense here on the left-hand side of the graph. Here we would always have increasing slope. If we just put a line somewhere here, it might be flat, but it's still increasing. And in the same way, if we have a positive value for x, this will still be positive, but this will be a negative number, so the slope would be falling. So it would be a negative slope, and this makes sense here on this side because it's there, it's going down basically, but flatter and flatter and flatter, as we shall see here. But yeah, so this is just a very simple example of this. Okay, finally, the last big thing I want to tackle in this section, maybe I want to tackle this on a new blackboard, I just think, is the derivatives of inverse functions. Because these we haven't talked about. We've seen that the inverse functions of continuous functions are continuous under good conditions, especially on intervals. So there we know if we have a continuous function, the inverse is again continuous if it behaves nicely. But here, for differentiability, we also have to prove this, but we will see again, it turns out well, it works. So first of all, we need an interval with more than one point, otherwise there will be some technical issue later on. So a non-trivial interval, of course, otherwise this would be very boring. Now we take a function from I to R, so again sticking with the real case as we did for the continuity issues. This should be continuous and strictly monotonic. In particular, we've seen that it's injective. This was the condition that we needed to have the continuity of the inverse map. And we let J be defined as the image of F. Okay, now if F is differentiable in some point A in I, and with one assumption, the derivative should be non-zero. If this is the case, then f to the minus 1 is now mapped from J to I. This is differentiable in the point f of A, which I will call B, such that the following holds. The derivative of f to the minus 1 in B is 1 divided by f, the derivative of f in A. And if you just want to purely write this in terms of B, this becomes a bit more messy, as is f prime at the point f to the minus 1 of B. Okay, let's prove this. We again need this alternative characterization theorem 4.6 for differentiability. Oops. So, proof. And now it's basically the same thing I did as in the chain rule. So, f is differentiable in A. So, by theorem 4.6 again, there exists a map R from I to C continuous with R of A is f prime of A, and such that f of x minus f of A is R of f of A, f of x, sorry. No, R of x, what am I doing? R of x times x minus A. This is what I want. Okay, so we have such a continuous map. Now, since, first of all, we know that, if x is equal to A, then we would have R of A, which is f prime of A, such that R is non-zero. If x is not equal to A, then we know from the strict monotonicity that this difference here cannot be zero, because these two values cannot be the same, since strictly monotonic functions are injective. So this is non-zero, which means that both of these factors, I mean this is obviously non-zero then, but this also has to be non-zero. So, since f prime of A is non-zero and f is strictly monotonic, This means that r of x is not equal to 0 for all x in I. Okay, this here also, sorry, this holds for all x in I. But if this is non-zero, then we can reformulate this thing from before, namely we switch it, we bring it to the other side, namely x minus a is 1 divided by r of a times x, f of x minus f of a. For all x in I. But now, since f is bijective, we can just replace everything by its images under f to the minus 1. Namely, this then implies that x is some element in I, so x can be written as f to the minus 1 of y, where y is some point in j. And here this is f minus 1 of b, which I will call b was just defined to be f of a. So this is equal to 1 over r of a times, and now here we get y minus b, simply in this way. This must be because this is bijection. So this is the case for all y and j. But sorry for the cut, I made another tiny mistake. So a is the same as f to the minus 1 of b. So we can insert this here as well. So this is r of f to the minus 1 of b. Now, by the theorem about continuity of the inverse functions, this was number, have I written this down? 323. F to the minus 1 is continuous in B. So this means the composition here, just by assumption on R, this is continuous in B. Okay, and now, so we have a continuous function here, which is continuous at that point. So now we can just apply theorem 4.6, but the other way around. Now we can derive the differentiability, derive, I should be careful with this word. We can conclude the differentiability of f to the minus 1. So now, by theorem 4.6, f to the minus 1 is differentiable in B with derivative given by this function here at that point. So f to the minus 1 prime of b is now the same as 1 over r, r of a, that is right, this again, and by assumption this was 1 over f prime of a, and this is what we wanted to show. So this already proves the claim. Okay. Now, this is now interesting because we've seen quite some functions which are inverse functions of others, and we shall now compute some derivatives of them. Okay, example for 14. Okay, let's do some computation. The first interesting inverse function that we basically considered always was the logarithm, the natural one, because the other ones are boring. So this is now going from r to infinity to r, 0 to infinity to r, and this is the inverse function of exp. By the previous theorem, so by theorem 413, log is differentiable. And we get as derivative log prime of x. So this is now by definition 1 of the, so if this is f minus 1, we need the derivative of f. So in this case f is exp. So we get exp prime at the point log of x. And as we've seen before, exp is just, x prime is exp itself. So we get 1 over exp of log of x, and of course these cancel each other out. So this is just 1 over x for all x in 0 to plus infinity. Okay, very simple. This we can now use to define, to compute a further class of derivatives, which is not directly an inverse function, but it involves a logarithm. And let me just include this at this point. Namely, if we take a in C be a complex number, so some arbitrary number, and we let f go from 0 to infinity to c, and we simply take f of x to be x to the power of a. So now for general powers, we've seen natural exponents, we have seen minus natural exponents so far, we've computed them, but here now we can compute a formula for general powers. Now then, since just by definition, if we recall how these powers are defined, this means that f of x is now given as x of a times log x. And we've seen that, yeah, log is differentiable, so x is differentiable. We have the chain rule. It follows that, so it follows by the chain rule that f prime of x, so this is now the derivative of x here, so x prime of a times log x multiplied with a times log prime of x, and now we've seen multiplying with constant numbers doesn't matter, and log prime is of course as we've seen 1 over x, so x prime is this is itself, so we get that this is x of a log x times a divided by x, and this is of course again x to the power of a. So what we get is a x to the a divided by x, and this gives a times x to the a minus 1. So we've got it. Sorry, I just said something wrong, so I quickly cut in. So this really gives this, shows that this formula that we had for powers with natural exponents or minus natural exponents, which was just the same formula here, that this really generalizes to all possible exponents. So this is kind of the general rule to derive powers. Okay, so the next thing we're going to tackle is the arc functions of sine, cosine, and tangent. Don't be irritated, I didn't change clothes after erasing for the big finale. Simply recording this on a different day, that's why I'm wearing different things for this final minutes. So I want to see some more examples of inverse functions, and the next thing we want to tackle is the arctangent. So we've constructed this as the inverse function of the tangent, and the tangent has been derived in this video. We've seen that the derivative of the tangent is 1 over cosine squared, which is, since the tangent is only considered on the interval of minus pi over 2 plus pi over 2, where the cosine is positive, so this is well defined. And what's important for our application of the theorem, this expression is non-zero everywhere, so for all x in pi over 2 minus pi over 2. This then implies that the arctangent, since the tangent maps everything to all of r, and so this is really bijection here, so the derivative of the arctangent can be directly computed by the previous theorem. So by a theorem for 13. Okay, it follows that arctan is differentiable. And we have the formula for the derivative. This is simply the arctan of x, arctan prime of x is 1 over the derivative of the tangent at arctan x. And so by this formula, this is the same as the cosine squared of arctan x. Okay, this is not that beautiful actually, because this cosine squared of arctan, this is okay, but we can simplify this by a lot, as we shall see. Namely, we just need a little computation with trigonometry. So we define y to be arctan of x. So, or in other words, x is the tangent of y. Okay, now we make a nice little computation. Then we can compute x squared is the tangent of y squared, which is by definition of the tangent the same as sine squared of y divided by the cosine squared of y. Oops. Y. So, since we know that sine squared plus cosine squared is 1, we write the numerator as 1 minus cosine squared of y divided by cosine squared of y. And this is the same as if we just decompose this, we get 1 over cosine squared of y minus 1. Okay, now we can do a little arithmetic. We just put this 1 over to the other side. So we get that And yeah, if we just put this 1 to the other side, we got x squared plus 1. And if we then take inverses, we get that 1 over 1 plus x squared is the same as, and now we get the inverse of this fraction here, so it's the same as cosine squared of y, and this was by definition the same as cosine squared of the arctan of x, and this is the term appearing in our derivative. So this then shows that the arctan prime of x is the same as 1 over 1 plus x squared, and this holds for all x in R. This is a beautifully simple derivative, and this will become also very important when we consider integrals of rational functions, where this is kind of really one of the base cases that appears in integration. So there we will use the arctan quite a lot, as we shall see, but this is just a derivative. That's something you have to keep in mind. That's quite important. Okay, that was the arctangent. Now let's come to the arcsine. So the arcsine goes from minus 1, 1 to minus pi over 2, pi over 2. And this is the inverse function of the sine restricted to minus pi over 2, pi over 2. We've seen that there it's strictly monotonically increasing. And there we've seen that since this is what we need to check, and you check that the derivative of the sine is non-zero in the inside of this interval, so we will not consider the boundary points here, but just the open interval from minus pi over 2 to pi over 2. Namely, since sine prime of x, we've seen that this is the same as cosine, and as argued before, this is non-zero for all x between minus pi over 2 to pi over 2, with boundary points excluded. Since this holds, it follows that the arcsine is differentiable. So it follows, by theorem 413 again. Let me just add this to make this clear. By theorem 413, that the arcsine is differentiable in, and we've seen that the arcsine maps the boundary points to the boundary points, so it follows that in every preimage of these, which is just the open interval from minus 1 to 1, so this is differentiable in every x in minus 1, 1, and we get a formula for the derivative. And so this is also a nice little formula, namely by construction, by this computational rule from theorem 413, the arcsine prime of x is the same as 1 over sine prime of arcsine of x, and we've seen that sine prime is the cosine. So this is 1 over cosine of arcsine of x. Okay, this is another expression that we want to simplify. Namely, now we can use our favorite equation that sine squared plus cosine squared is 1. So we know not only that the cosine is non-zero, but we know that it's positive on this interval that we're studying. So since the cosine of x is bigger than 0 for all x in minus pi over 2 to pi over 2, it follows that the cosine of x is, so we know that the sine squared plus the cosine squared is 1. Then we know if the cos is positive that this is plus the root of 1 minus sine squared. We choose different variables, say cos t is the same as the square root of 1 minus sine squared over t for all t in this open interval from minus pi over 2 to pi over 2. Okay. So if we insert this in the previous equation, we see that it becomes much simpler. So the arcsine prime of x is 1 over, and now square root of 1 minus, so the sine of arcsine of x, and now I'm writing the squared at the end. So you can see what's happening. This is obviously just by definition, this is x. Oops, forgotten the square root here. Okay, like this. So this becomes 1 over square root of 1 minus x squared. So this is again a very simple formula. Okay, and we see that we have surprisingly simple derivative for a quite complicated function. So in the same way, you can derive the arc cosine, which I don't want to do. And the only difference is basically you do the same with reversed roles of sine and cosine. The only thing where just the difference occurs is that the sine, the derivative of the cosine that would appear here then is not the sine but minus the sine, which gives another sign in there, another minus sign. And one obtains that the arc cosine prime of x is minus 1 over the square root of 1 minus x squared for all x in minus 1, 1 again. Yes, okay, yeah. Okay, so this I won't do, but this is the same computation basically, and we just get a sign change. Okay. Okay, great news. So meanwhile, we now have derivatives of basically all our favorite functions, of all the functions we use to construct other functions. And now using the product rule, the chain rule, and the other rules we've seen in this section, we can just derive a lot of function. And this basically, I can give you arbitrarily complicated functions consisting of all the stuff we've seen before, of powers, of trigonometric functions, exponential, whatever, logarithms. And we can now derive everything. We just have to go by the rules and do it one by one by one and integrate this straightforwardly by the rules. Okay, so now we know how to differentiate everything. And in the next section, we will see quite some applications of differentiability and what you can kind of do with differentiability and how it's connected to some terms we've seen before. See you in the next video.